Hello, my name is Sharon Mozgai. I'm the director of the Virtual Human Therapeutics Lab at USC's Institute for Creative Technologies, and today I'm presenting our case study on the design of a research tool that accelerates the scoping review process. My co-authors listed here include Kaurloto, Jade G. Winn, Andrew Leeds, Sarah Beland, Arman Sookiassian, and Arno Hartholt. This team is made up of computer scientists, librarians, and social scientists. We initially began working together to conduct a literature review on virtual human fidelity or realism. And this review is still in progress, but along the way, we realized we had a unique opportunity to apply machine learning techniques to rapidly map the last 30 years of virtual human research and automate some of the more tedious parts of a scoping review. I'll be giving a high-level overview of our methodology a little later in this talk. Virtual humans are digital embodied interactive characters that are scalable, available 24/7, and customizable. Virtual humans are fundamentally computer programs, code and data designed to give the illusion of a human being. As I mentioned, our team is from ICT, and we have a rich history of making virtual humans for various purposes, to heal, teach, train, and entertain. But one question that inevitably comes up for every project is what level of virtual human fidelity, also known as realism, is optimal for the desired interaction. So when we think of virtual human realism or fidelity, our mind may automatically go to rendering style. Is it photorealistic or is it more cartoonish? But really, we need to consider virtual human fidelity across multiple domains when designing an interaction. This can include nonverbal behavior like facial expressions or gaze, verbal behavior such as the quality of the voice, and even social fidelity such as whether or not the virtual human has command of social norms or politeness. For these reasons, when we set out to attempt to answer the general question, what level of fidelity or realism is best for virtual humans, we thought it was imperative to review the extant and lit to ultimately classify the relationships between types of fidelity, the purposes of the virtual humans, how researchers measure and evaluate the impact of fidelity, and who the virtual human is meant to be interacting with. So our team at ICT partnered with experts from USC libraries, and we collectively decided that the type of literature review best suited for this project would be a scoping review. Scoping reviews have the general purpose of identifying and mapping available evidence in a topic or field. Unlike systematic reviews, which you may be more familiar with, scoping reviews are guided by the requirement to identify all relevant literature, regardless of study design. Most published scoping reviews follow the 5-stage process initially defined by Arksey and O'Malley that includes identifying a guiding research question, identifying relevant studies, study assessment and selection, mapping the data, and summarizing and reporting the results. Here is the search criteria we used for our scoping review. It was apparent early on that we would need to cast a wide net in order to capture all the relevant literature. Not only are there multiple terms for virtual human fidelity, but experiments on fidelity can be conducted without any of these terms being used in the title, abstract, or body of the paper. There are also multiple ways in which researchers and industry refer to what we call virtual humans. So we mined 13 databases and pulled journal articles, conference proceedings, dissertations, and review articles on virtual humans, digital humans, embodied conversational agents, and virtual agents published between 1990 and 2022. This search resulted in over 30,000 articles. At this stage in our scoping review process, we've realized that we had a unique opportunity to map the last 3 decades of virtual human research. So while we were reviewing the large dataset manually for articles specifically related to fidelity, we decided to leverage the machine learning expertise on our team to attempt to map the field and automate portions of the 5-step scoping review process. The ISR framework we use to guide this work conceptualizes the design process as an embodiment of 3 closely related cycles of activity: relevance, rigor, and design. In the relevance cycle, the subject matter experts on our team reviewed the 5-stage scoping review process and indicated that automation could potentially expedite stage 4, charting the data, and stage 5, summarizing and reporting results. Here, we also defined 4 areas that were determined to be of high priority for any research tool we developed, namely replicability, objectivity, automation and scalability, and the ease of discovery for non-computer scientists. In the rigor cycle, we reviewed the literature on evidence synthesis techniques. We found document representation algorithms relying on extremely large datasets and neural network models that are capable of representing complex relationships across sentences, as well as entire documents, and this seemed particularly salient to our dataset that included the title and abstracts of over 30,000 papers. Moving on to the design cycle, I will walk you through our ultimate process. First, we leveraged the state-of-the-art document-level representation learning method, Spectre, trained directly on our academic paper titles and abstracts to derive high-dimensional numeric representations for each document. Next, we employed TISNI, a dimensionality reduction algorithm to enable the visual inspection of the relationships between papers. We then used the well-known k-means clustering algorithm to cluster documents into topics. To identify the optimal number of clusters, we used the elbow metric. To label each of these clusters, we used a word cloud algorithm. There, 2 subject matter experts stepped in and independently examined each word cloud manually to identify topic names and keywords. They then discussed their findings in order to determine the final topic labels. The labeling of these clusters took approximately 5 hours of work per reviewer. Here is an example of 4 of the word clouds that were visually inspected. Subject matter experts pulled keywords from each of these plots to home in on a topic label. And here is the full list of our 29 clusters. As you can see, this method allowed us to quickly map the broad field of virtual human research. For example, 2 topics with some of the largest number of publications and greatest year-over-year growth include social behavior and machine learning. We were also able to quickly visualize and compare the year-over-year growth for various clusters. Here you see healthcare and animation clusters, respectively. Healthcare is shown in blue with a rapid growth trend, and animation is shown in purple with a longer history in the field and a slower decline over the more recent years. Additionally, we could also use this method to rapidly identify gaps in the literature through keyword searches. Here you can see the search for papers directly related to the military use of virtual humans represented in orange. So this can be interpreted as a limited number of articles on this topic that are spread out across topic clusters. And here's our tool, a semantically organized interactive evidence map clustered by salient topics. To enable replicability, we provide full access to the dataset, this interactive evidence map, and source code on GitHub. Let me show you how this works. Each of the 30,000 plus articles are represented by a point on this interactive map that provides information like title, author, and publication year. All cluster names are provided on the right-hand side of the screen, and you can toggle these names on and off for ease of navigation. Additionally, you can link directly to Google Scholar. This project would not have been possible without a multidisciplinary team. As this was a multidisciplinary effort, we spent multiple sessions early on in the process cross-training our specialized expertise, which created a base-level knowledge of literature reviews, library sciences, virtual humans, and machine learning techniques across team members, which aided communication, workflow, and report writing. The ISR framework carved out a path that everyone on the team could understand across discipline and help us to cultivate a feedback loop across the ISR process. This work isn't without its limitations. Though our first aim is replicability, this step may be daunting for teams without some level of computer science knowledge. And while our semi-automated approach speeds up data synthesis, it still requires the qualitative analysis of clusters by subject matter experts. When using the elbow method, researchers should apply their own judgment when assessing the exact number of clusters and may need to discuss merging or splitting clusters given the observation of subject matter experts. It should also be noted that a filtering approach could be introduced as a next step and evolution of this tool. Here is my contact information if you have any questions for me and the location of our GitHub repository. I want to thank you for your time.